Hello, my name is Chang. Today I'll present our research on EEG spectral band analysis in mental health, focusing on insights gained through explainable AI in functional connectivity. This work was conducted at the University of Wisconsin-Madison. Our research addresses the critical need for the objective biomarkers to improve ADHD diagnosis. Current neuroimaging and diagnostic tools often fail to provide clear distinctions in ADHD-related neural activity, especially in terms of emotional and cognitive processing. We focus on analyzing EEG spectral bands, particularly theta and beta frequencies. These bands are crucial because the theta over beta ratio has been consistently associated with ADHD-related cognitive and emotional regulation difficulties. To achieve this, we utilized EEG data that underwent pre-processing for noise reduction and then applied a functional connectivity analysis. Using an explainable AI framework, we constructed connectivity graphs and emotion distance matrices to identify key patterns. Our goal is to uncover distinct connectivity differences between ADHD and non-ADHD individuals. Analyze emotion distance matrices to identify differences, providing insights into the disorder's neurobiological aspects. Attention deficit hyperactivity disorder, also known as ADHD, is a neurodevelopmental disorder marked by persistent inattention, hyperactivity, and impulsivity. It affects individuals across all age groups and significantly impacts cognitive functions, emotional regulation, and social interactions. With the increased prevalence of ADHD, there is a growing need for effective diagnostic and therapeutic interventions. Our research aimed to address this by delving into the disorder's neurobiological foundations to better understand its underlying mechanisms and pave the way for improved strategies in diagnosis and treatment. So EEG is a non-invasive method widely used in ADHD research to measure brain activity patterns. In the context of ADHD, two specific spectral bands, theta, which ranges from 4 to 8 Hz, and beta, which ranges from 13 to 30 Hz, are particularly significant. Research has shown that the theta over beta ratio can serve as a potential biomarker, as individuals with ADHD often exhibit an elevated ratio compared to non-ADHD individuals. This elevated ratio is closely linked to deficits in attention, cognitive control, and arousal regulation. Such anomalies in these bands reflect ADHD's impact on the neural networks that support cognitive and emotional processing. Our study design involves three key components. First, we analyzed two groups of participants, individuals diagnosed with ADHD and a control group of non-ADHD individuals. Secondly, we collected EEG recordings to measure brain activity across multiple channels. This data was carefully pre-processed to ensure accuracy and focus on the theta and beta frequency bands, which are critical for understanding ADHD related to neural activity. Lastly, we examine brain connectivity during four distinct emotional states: angry, happy, neutral, and sad. This approach allows us to compare functional connectivity patterns between the two groups and explore how ADHD impacts emotional cognitive processing under different conditions. Our methodology begins with EEG data acquisition, where recordings were collected using standardized protocols. The dataset is publicly available. These recordings captured brain activity across multiple channels and were segmented into epochs that represented different emotional states, like angry, happy, neutral, and sad. The data were further processed to isolate the theta and beta frequency bands. In the data pre-processing step, we filtered the raw EEG signals and to remove noise and artifacts. This step was critical for ensuring the accuracy of functional connectivity calculations, and narrowing the analysis to the theta and the beta bands. And then we conducted the functional connectivity analysis, which involved two key components. First, we compute functional connectivity matrices using Pearson correlation to measure statistical dependencies between EEG signals from different channels. These matrices provided insights into interrelationships within and between brain regions. Second, we applied independent component analysis, or we call ICA, to extract independent neural components. These components were then used as nodes in subsequent graph-based connectivity analysis, forming the basis for identifying distinct ADHD patterns. Our methodology also includes XAI graph creation and statistical analysis. Using the selected SI components, we constructed XAI graph for each emotional state: angry, happy, neutral, and sad. And for the theta and beta frequency bands, these graphs represent coherence values between neural components, highlighting functional connectivity patterns in the brain. Different graphs were created for ADHD and non-ADHD groups, allowing us to focus on how their connectivity differs. Next, in the statistical analysis, we analyzed the XAI graphs to identify connectivity differences between ADHD and non-ADHD groups. We computed emotion distance matrices to capture dissimilarities in the brain connective across emotional states. Statistical measures then quantify these differences, providing a basis for interpreting how ADHD impacts neural connectivity and emotional processing. Our functional connectivity analysis revealed distinct differences in connectivity patterns between ADHD and non-ADHD groups, particularly in the theta and beta bands. Here, the bar chart shows graph distance for emotions like angry and happiness across frequency bands. For example, we observed that the ADHD group exhibited elevated gamma band connectivity compared to the non-ADHD group. This suggests altered functional connectivity, especially in regions associated with cognitive and emotional processing. These findings align with previous research on elevated theta over beta ratios in ADHD. Extending the analysis to neutral and sad emotional states, we continue to observe similar trends in gamma band connectivity as a distinguishing factor between ADHD and non-ADHD groups. As shown in the bar charts, the ADHD group consistently demonstrates higher graph distances in gamma connectivity, suggesting an altered emotional processing network. The XAI graphs here provide a detailed visualization of connectivity patterns for the beta frequency band across ADHD and non-ADHD groups. The graph on the left represents the ADHD group, while the one on the right shows the non-ADHD group. These graphs highlight coherence value between XAI components, illustrating how neural circuits interact. Notably, the ADHD group exhibits distinct connectivity patterns with reduced coherence in some connections, suggesting potential impairments in cognitive control and emotional regulation. These findings reinforce the hypothesis that beta band connectivity is a key differentiator between ADHD and non-ADHD individuals. And theta band connectivity patterns for ADHD and non-ADHD groups. The ADHD group demonstrates more dispersed connectivity, which could indicate dysregulation in attention-related neural networks. This contrasts with the more concentrated connectivity observed in the non-ADHD group. These findings suggest alterations in the theta band connectivity play a critical role in the neural characteristics of ADHD, affecting attention and emotional processing. Here are the presents the emotion distance matrices for both ADHD and non-ADHD group. These matrices highlight the differences in connectivity patterns across emotional states. On the left side, we can see the non-ADHD group, which shows more distinct separation between emotions, represented by higher contrast in values. In contrast, the ADHD group, displayed on the right, exhibits less distinct separation between emotional states, suggesting potential difficulties in emotional processing. The most significant differences are observed in the theta and beta bands, aligning with the findings that these bands are crucial in ADHD-related disruptions in emotional regulation and cognitive control. Here we present the statistical results summarizing the graph distances across frequency bands and emotional states. The table quantifies the differences between ADHD and non-ADHD groups for delta, theta, alpha, beta, and gamma bands. Notably, the gamma band shows the largest differences across all emotions, particularly in angry and sad. This supports our earlier findings that gamma band connectivity is significantly altered in ADHD. Similarly, theta band connectivity differences further reinforce the role of this oscillatory pattern in distinguishing ADHD-specific neural characteristics, especially in emotional and cognitive processing. Our study uncovered several significant findings that shed light on the neural characteristics of ADHD. We observed increased theta connectivity in ADHD individuals, which aligns with the previous research linking elevated theta activity to attention deficits and challenges in cognitive regulation. This reinforces the role of the theta over beta ratio as a key biomarker in ADHD. Beta band alterations were also prominent, with disrupted connectivity in regions associated with emotional regulation and suggesting impairments in these critical cognitive functions. Additionally, we identified distinct differences in emotional processing, as evidenced by reduced differentiation of emotional states in the ADHD group, which was most evident in emotional distance matrices. These matrices highlighted a less distinct separation between emotional states, pointing to potential difficulties in emotional recognition and regulation in ADHD. Furthermore, graph distance analysis revealed key disparities in brain connectivity patterns across different frequency bands, particularly in the theta and beta bands, emphasizing the neurosociological differences between ADHD and non-ADHD groups. Finally, statistical analysis confirmed these findings, demonstrating significant differences in connectivity matrices across all measures. These results not only validated previous research, but also offer new insight into the interplay between cognitive and emotional processing in ADHD, providing a foundation for targeted interventions and further study. Our findings provide significant clinical implications for understanding and managing ADHD. The observed differences in the theta and beta band connectivity suggest their potential as diagnostic biomarkers, aiding clinicians in objectively identifying ADHD. These biomarkers could also facilitate treatment monitoring, allowing them to track changes in neural connectivity during interventions. Furthermore, the results open avenues for personalized therapeutic approaches, such as neurofeedback interventions. By targeting theta and beta band activity, these therapies could improve attention and emotional regulation in individuals with ADHD, offering solutions based on each patient's unique neural profile. Let's now discuss the limitations and the future directions of this study. Firstly, the sample size was a key consideration. A larger dataset is essential for more generalizable results. technical constraints such as the use of specific neuroimaging model limit the depth of connectivity insights. Moving forward, future research should emphasize longitudinal study to explore how ADHD connectivity patterns change over time, multi-model integration to incorporate advanced imaging techniques, and clinical validation studies to ensure practical applications in diagnosis and treatment. Addressing these limitations will enhance our understanding and pave the way for impactful, personalized interventions for individuals with ADHD. In conclusion, our findings highlight the distinct brain connectivity patterns associated with ADHD, particularly within the theta and beta bands. These patterns reflect alterations in neural oscillatory behavior that contribute to cognitive and emotional regulation challenges. Emotional processing differences and connectivity matrices not only deepen our understanding of ADHD, but also offer potential biomarkers for diagnosis and treatment. These insights emphasize the importance of personalized diagnostic approach and targeted interventions. However, this study also highlights the need for future research to address limitations, such as sample size and technical constraints, and to validate findings through longitudinal and clinical studies. Thanks for listening.